Subgradient methods are a class of iterative algorithms designed to minimize convex functions that may not be differentiable everywhere. These methods share similarities with classical gradient descent, but they incorporate distinct features to address the challenges posed by non-differentiability. They offer a practical approach to solving optimization problems where standard gradient-based techniques are not directly applicable. Subgradient methods have their origins in the Soviet Union during the 1960s and 1970s. Researchers like Shor and others developed these techniques to address optimization problems that could not be effectively solved using traditional gradient-based approaches. The primary motivation was to handle non-differentiable functions, which arise in various applications. A key advantage of subgradient methods is their ability to directly handle functions that are not differentiable at every point. Unlike standard gradient descent, these methods do not rely on the existence of a gradient everywhere. Instead, they employ the concept of a subgradient, which is defined even at points where the function is non-differentiable, enabling optimization to proceed. Subgradient methods exhibit several key differences compared to classical gradient descent. Notably, they are not strictly descent methods, meaning that the function value may occasionally increase during iterations. Furthermore, step sizes are usually predetermined using specific formulas rather than being adaptively chosen through line search procedures as in standard gradient descent. In subgradient methods, the step sizes are typically predetermined using various strategies, contrasting with the line search methods often employed in gradient descent. Common step size selection strategies include using a constant step size, a diminishing step size sequence that satisfies certain conditions, or the Polyak step size, which requires knowledge of the optimal function value. A notable characteristic of subgradient methods is their potential for slow convergence, particularly compared to gradient descent, especially when dealing with ill-conditioned problems. The convergence rate is highly sensitive to the choice of step sizes, making their careful selection crucial for achieving acceptable performance. The subgradient method is designed to solve optimization problems of the form minimize f(x), where f is a convex, proper, and closed function. Importantly, f is not required to be differentiable everywhere, making subgradient methods suitable for a broader class of problems compared to traditional gradient-based approaches. The subgradient method proceeds iteratively. Starting with an initial point x and a chosen step size sequence alpha, at each iteration k, a subgradient g is selected from the subdifferential of f at x. The update step then moves the current point in the direction opposite to the subgradient, scaled by the step size, x equals x alpha g. This process repeats until a suitable stopping criterion is met. For the subgradient method to converge, certain assumptions must hold. First, the objective function f must be convex and possess a finite minimum value f star operator, which is attained at some point x star operator. Second, the subdifferential del f, x, must be non-empty for all x encountered during the algorithm's execution. Finally, the subgradients must be bounded in norm, meaning there exists a constant g such that is parallel to g is parallel to less than or equal to g for all iterations k. One strategy for choosing the step size is the Polyak step, defined as alpha equals f x f star operator slash is parallel to g is parallel to superscript 2. This step size aims to optimize convergence, but requires knowledge of a lower bound f star operator on the minimum value of the objective function. In practice, f star operator is often estimated or set to a reasonable value like 0. Using the Polyak step size, we can analyze the convergence properties of the subgradient method. Specifically, the distance to the optimal solution decreases at each iteration, leading to a convergence rate where the minimum value of f x f star operator over all iterations k is bounded by rg /square root n, where r is a bound on the initial distance to the optimal solution and g is a bound on the subgradient norm. When a constant step size alpha equals alpha 0 is used, the subgradient method converges to a neighborhood of the optimal solution, rather than converging exactly to the minimum. The size of this neighborhood is proportional to g superscript 2 alpha/2, where g is a bound on the norm of the subgradients. Therefore, a smaller constant step size leads to a smaller neighborhood around the optimal solution. To ensure convergence to the optimal solution, diminishing step sizes can be used. These step sizes must satisfy the Robbins-Monro conditions. Alpha must be greater than 0 for all k and converge to 0. The sum of alpha must diverge to positive infinity, and the sum of alpha squared must converge. A common example of a step size sequence satisfying these conditions is alpha equals a/k plus 1, with a greater than 0. The normalized subgradient method modifies the standard update rule by normalizing the subgradient. The update is given by x equals x, eta, g slash is parallel to g is parallel to, where eta is a step size. This normalization helps to adapt the step size to the magnitude of the subgradient, potentially improving convergence behavior. For constrained optimization problems where we want to minimize f(x) subject to x belonging to a convex set C, the projected subgradient method is used. First, an intermediate point y is computed as x alpha g. Then, this point is projected onto the feasible set C to obtain the next iterate x. The projection p_c, y, finds the closest point in C to y. Subgradient methods find applications in machine learning, particularly in solving L1 regularized problems like Lasso regression. The Lasso problem involves minimizing a combination of the residual sum of squares and the L1 norm of the weight vector. Since the L1 norm is non-differentiable, subgradient methods are well suited for this task. The subgradient of the L1 norm is the sine of W, with values in the interval -1, 1 at zeros, and projected subgradient methods can promote sparsity by automatically selecting relevant variables. Subgradient methods are also used in training support vector machines, SVMs. The primal SVM formulation involves minimizing a combination of the weight norm and a hinge loss function. The hinge loss is non-differentiable, making subgradient methods a natural choice for optimization. Additionally, box constraints on the variables can be handled using projected subgradient methods. Online subgradient methods are designed for sequential or adversarial learning scenarios. In this setting, at each round t, the algorithm makes a prediction x from a convex set C. Then, the environment reveals a convex cost function f. The algorithm incurs a loss f, x, and observes a subgradient g from the subdifferential of f at x. This information is then used to update the prediction for the next round.